Okay students, welcome to this 16th session of this workshop, and today I am going to talk about the discrete time counterpart of the Laplace transform, right? And this Z transform is as widely used now because most of the systems that we use now are digital systems, right? Since the computation using discrete digital sequences is very simpler, right? So we can use different computing devices. Okay, we have application specific devices as well as general purpose devices for the this computation. Okay, so that is the significance of Z transform. Okay, one of the motivations to study Z transform, because we model discrete time systems using the difference equations, and ultimately we go into the transform domain and use Z transforms for the analysis. Okay, so it's equivalent to Laplace transform, just that it's applied for a discrete time systems or discrete systems. Okay, now so one thing that I didn't deliberately mention. Okay, so we have discrete time counterparts of complex exponentials as well. Okay, so we have sequences of the form z power n, okay, where z is nothing but r e power j small omega. Okay, so I used this capital omega for analog frequency. Okay, and this omega is your digital frequency. Okay, and the units for both of them is different. Okay, so this is just radians, a dimensionless quantity. Okay, and analog frequency is radians per second. It has dimensions of per second. Okay, now okay, fine. So now if we take a system, an Lti system, okay, this is just an extension of what we have studied for analog systems. Okay, so the Lti systems are characterized by something called as impulse response. So as you assume, we know the impulse response of this Lti system that I have drawn. Okay, and suppose if I feed z power n as an input, and we'll see what the output is. Okay, so we know that the input output relation, so if this is the input, so let y of n be the output, and we know that for an Lti system the input output relation is given by the convolution sum relation. Okay, I'm going to use h of k and x of n minus k, right? I told you that this is commutative, the convolution sum relation is commutative, so I'm going to use this, and this is the relation which is more helpful than the other one, x of k into h of n minus k, summation k going over to from minus infinity to plus infinity, right? So to do the manipulations. Okay, so this is h of k z power n minus k. Okay, so if I separate them out, so what I get is, since the summation is over k, okay, so z power n I can take it out, because z power n minus k can be written as z power n into z power minus k. Okay, so this is h of k z power minus k, right? When you sum it over k from minus infinity to plus infinity, right, so the term in the bracket here will just be a single number whose value depends on the value of z, the complex number. Okay, now so I can write y of n as some number whose value is dependent on z. So I indicate the dependence by this term h of z, right? It will be a function of z, right? So as z varies, the value of h of z will vary into z power n. Okay, so what is happening here is, so we see that whenever we feed a complex exponential to an Lti system, discrete time system, okay, so it gets, the output will remain the same as input, but it will be scaled by an amount h of z. Okay, so z power n, the complex exponentials, right, discrete time complex exponentials, are eigenfunctions again, right? So you can see the one-to-one relation between the Laplace transform and Z transform here, right? So e power st was a complex exponential in a continuous time case, and they were the eigenfunctions of continuous time LTI systems, Z power n for discrete time systems, and this h of z, right, is the corresponding eigen value. Okay, so you go on varying the value of z, right? So the corresponding eigen value also varies. Corresponding eigen value. Okay, so the output, whenever you feed a complex exponential to the system, to an LTI system, right? What happens is the output will be of the same form, except that it will be scaled by certain amount whose value depends on z, in this case s in the continuous time case. Okay, right? Okay, so this h of z, this relation, right, so I can use k, n, m, p, q, it doesn't matter what I use inside the bracket, ultimately it's going to vanish. Okay, so if I use, let's say, p, so it doesn't matter. Okay, so why I call this as a dummy variable, I'll explain it now. Okay, so this is same as, okay, so before that, what is this summation giving you? This is called as a Z transform, and by the conventional notation for the term inside the bracket is n of sequence h of n. Okay, now if why is this p called as a dummy variable is, right, so if I expand this summation, this will be nothing but so I have infinite terms on the left and infinite terms on the right. Okay, so this I can also write it as summation k going from minus infinity to infinity h of k z power minus k. Even if you expand this, so you're getting the same expression here. Okay, so k or p, they are called as running variables or dummy variables. Ultimately, when you evaluate the summation, okay, with the specific value of z, right, so it's ultimately going to be some number. Okay, so this is what I mean, that is why we call this p or k as a dummy variables. Okay, now as we had complex plane in terms of a Laplace transform case, here we have something called as a it's also a complex plane, but we represent point in a different form, right? So s was sigma plus j omega, the capital omega, where it we called it as a rectangular form of a complex number. Here we are representing the complex number in a polar form. Okay, so the only difference is there we had rectangles, here we have circles. Okay, right? So if you keep, this is nothing but your r, and this is omega, and this point here is r e power j omega. Okay, if r is equal to 1, the radius of the circle will be equal to 1. Okay, it's called as a unit circle. Okay, now fine, this is called as a z plane. Okay, so there we had here in this z plane we'll have circles, or they are called annular this one ring kind of structures. Okay, they are called annulus, I guess, right? Okay, fine, again the same thing, coming to the existence condition for existence of z transform. The theory remains the same, only we have summation here, we had integration there. So x of z as usual is defined as summation n going from minus infinity to infinity x of n z power minus n. Okay, so this is nothing but, so dot 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 sum of complex numbers is, right, complex numbers. So I don't know whether you have noticed it or not. So since out of habit we write it and we don't think it's significant, but all the time domain notations use small letter, whereas all the frequency domain notations or Z domain or Laplace domain notations use capital letters. Okay, so that is the convention that is followed, the standard convention. Okay, so this is just a complex number. So this is one complex number, this is another complex number, this is another complex number. X of n can be complex. Okay, it's not that it's always real. Okay, so this is another complex number, so on and so forth. Now coming to the existence, as I told you, if I take the mod, right, on both sides, this will be equal to mod of this. So go back and look at the previous lectures. Okay, so from the law of triangular inequality, if I take the modulus inside, right, so we saw that if z1, z2, z3 are the sides of a triangle that I had drawn, okay, so mod of z3 will be equal to mod of z1 plus z2. Okay, this is my usual law of triangular inequality, right? I had explained it in the previous lectures, just a small revision. Okay, so if I take the summation inside, so this is like summation of z1 plus z2. Okay, here we had only two terms, so I am going to write this z1 plus z2 in this form, k equal to 1 to 2 zk. Okay, mod, right? So when I take the mod inside, so this is nothing but mod z1 plus mod z2 can be written as okay, right? Fine. So the same thing I'm doing here. So when I take the modulus inside, so it's going to get, sorry, I'll write it below. Okay, so now we know that if what shall I call, if z is a product of two numbers z1 and z2, so mod of z will be equal to mod of z1 into mod of z2. So I am going to use this, so this will be less than or equal to summation n. So this is by law of triangular inequality, triangle inequality. Okay, so this is one of the important laws that you have to remember, inequalities. Okay, so mod x n into mod z power minus n. Okay, so what is mod of z power minus n? So what is z? Z is nothing but r e power j omega plus j omega. Okay, so mod of z is nothing but mod of this. What does mod give you? Mod gives you the length. Okay, the length of this radius r. Okay, so this is nothing but r. Okay, and what is if r is equal to 1? Okay, basically it's all the points that lie on the circle of radius 1. Okay, so the point is now identified by the value of omega. Okay, so now mod of z in this case is equal to 1, because mod of e power j omega is nothing but cos square omega plus sin square omega, right? So if I use that, so I will get so this I can take it inside, because r power minus n is always real, because length cannot be complex, length always has to be real. Okay, so r is always real, r power minus n is real, so I can take it inside. Okay, so this is what it's telling me. Fine. So the same example I'm going to take, which I did for Laplace explanation of Laplace transform, right? So let's take an example. Okay, so what is this telling you? This gives you the sufficient condition for existence of Z transform. Okay, so if the RHS is something finite, okay, then LHS is definitely something finite, okay, because it's less than or equal to the maximum value that it can be take is bounded by the RHS. Suppose if RHS is infinity, so we cannot tell with confidence that mod of x of z is definitely finite, okay. So it is a sufficient condition. If x of z is infinite, then we say that the z transform doesn't exist, okay. So if it's finite, then sure the z transform exists. It will be some number, okay, depending on the value of z, right? Now when will this x of z be less than infinity? When this term x of n into r power minus n summation will converge, okay, will be something finite, okay. Suppose if this term, this summation, if you evaluate, it goes something like this: 1 plus 2 plus 3 plus, just as an example, right? You can see that as you go on adding infinite number of terms, the sum is obviously going to blow up, right, to infinity, right? We say that this sum is diverging. Suppose if the sum goes something like this, what is this? This is a geometric series, okay, right? So on and so forth up to infinite terms. This obviously is going to converge, and what is its sum? It will be 1.2, okay, right? So this is something finite, whereas the previous one which I wrote, it's obviously getting diverged, right, and the sum will go to infinity, right? If sum goes to infinity, we say that the series is divergent. If sum is something finite, we say that it's a convergent series, okay. So series is nothing but summation of these terms, okay, and if there is a relation between previous term and the next term, right, so we have different progressions, right, arithmetic progression, geometric progression, and harmonic, okay. So this is kind of the example that I gave here, which you are seeing on the screen, is a geometric progression, okay. Okay, so an example, right, so x of n is given as a power n u of n, okay. So x of z by definition, so as I tell you, please have the habit of writing this summation n going from minus infinity to infinity, x of n, since a of n is multiplied by u of n, you can split it from n equal to minus infinity to minus 1, x of n z power minus n, plus n equal to 0 to infinity x of n z power minus n. The first term will go to 0 because u of n equal to 0 for n less than 0, right? So this will become n equal to 0 to infinity a power n z power minus n, okay. Now this I can write it as right, so this is nothing but 1 plus az inverse plus az inverse square plus so on and so forth, okay, right. So now when will this series be convergent? When az inverse is less than 1, okay. So suppose if az inverse is 2, az inverse, sorry, this will be a square z inverse square, okay, or so on and so forth, okay. So if this is 2, this is 4, this is 8, so on and so forth, obviously the series is getting diverged, okay. The sum will obviously go to infinity, right. So when will the sum be less than infinity? When az inverse is less than 1, right. So az inverse square is obviously less than 1, okay. So if you have some quantity lying between 0 and 1, when you take a square, it will be less than the original number, okay. So this series will get converged, okay. So if you evaluate the geometric series, then what do you get? 1 by 1 minus r, okay. What is r in this case? It's the ratio of the any two consecutive terms, okay. So az inverse by 1, right, az inverse square by az inverse, the that is what we call the common ratio, which is r, which is different from this interpretation of complex numbers, right. So this is 1 by 1 minus az inverse, Okay, and when is this true, right? So if AC inverse is greater than 1, what is going to happen? The series is getting diverged, the sum will go to infinity. When will the sum be equal to something finite? This is only when AC inverse is mod of this is less than 1, okay, or yes, mod Z is greater than mod A. Okay, so this is the case, and all the values of Z whose lengths are greater than the mod of value of A, right? So those set of points will come in the region of convergence. Okay, let's say, suppose say, if A is equal to let's say 2 plus J, what shall I use? Okay, let's use 3 plus J4. Okay, so what is mod of A? Mod of A is nothing but square root of 3 square plus 4 square, which is 5. So these are your Pythagoras numbers. Okay, now if you draw the Z plane, okay, you have a unit circle. So there the imaginary axis was the reference. We have a unit circle here. Okay, this circle is a reference. Now all the values of Z, okay, so the value depends on only a mod of Z, right? So we have this circle, right, and all the values that are greater than the set of all points Z which lie outside this circle. Okay, if you evaluate Z transform here, then the sum will be definitely finite. Okay, so if you evaluate x of Z somewhere here, okay, so you cannot tell whether the sum is going to converge or diverge. In this case it will definitely diverge. Okay, so you can try evaluating it. Let's take some point, okay, whose value mod value is less than 5. Take 2 plus J3, right, and evaluate the Z transform. It has to go to infinity. Okay, take Z equal to this and A, keep A equal to that. Okay, so it has to go to infinity. Fine. That's about region of convergence, so we'll stop here.